So today we're going to be talking about absolute value functions and graphs. How are absolute value functions related to piecewise functions? An absolute value graph is two linear functions x and negative x put together. So now let's graph the basic parent function of an absolute value. We know that anything underneath these absolute value bars automatically becomes positive. So if we put negative 3 in for x, we get absolute value of negative 3, which we know is just 3. Likewise, if we put negative 2 in for x, we get absolute value of negative 2, which is 2. Here we'll get 1, 0. When we put positive 1 in for x, the absolute value of positive 1 is still positive 1. Same for 2 and 3. Now let's plot these points. And here's our absolute value graph. Some key characteristics of our absolute value is that it is V-shaped, as you can see from what we just graphed above or down here. The highest or lowest point is called the vertex. This is also the minimum or maximum. Whether it's the minimum or maximum point depends on whether the absolute value is positive or negative. If the absolute value is positive, it's going to look like this. If the absolute value is negative, it just flips upside down and it'll look like that, like an upside down V. The graph is symmetric about the line x equals 0, which we know is also the y-axis, which just means, you see here, that if we were to draw a line right here, which is kind of already drawn for us since it's the y-axis, it splits the function in half and we have two equal parts on either side. If xy is on the graph, negative x, y is also on the graph. All right? All that means is when you have point 1, 1, you're also going to have point negative 1, 1. The graph is symmetric about the y-axis, which is the line x equals 0. We kind of already said this. The left half of the graph is a line with a slope of negative 1. The right half of the graph is a line with a slope of 1. Remember, this is talking about our parent function. These types of things will change once we start changing it a little bit. Our domain is all real numbers. Our range for our original parent function is y is greater than or equal to 0. Our graph is increasing from 0 to infinity, which you could also write like this. And it is decreasing from negative infinity until 0, which you can also write like this. Our zeros for our parent function is just 0, 0. You could have more than one 0 if the graph is moved around. Say you cross through the x-axis here, you would obviously have 2. So now we're going to be talking about some transformations of absolute value functions. So if the absolute value of a is greater than 1, the graph is narrower than the parent function. If the absolute value of a is less than 1, the graph is wider than the parent function. So pretty much what this means is if a is greater than 1, it's narrower. All this is saying is if a is a fraction, the graph is wider. And the reason why is because you know absolute value is never going to be negative, so if it's less than 1, it clearly has to be a fraction. The a value is the slope of the lines. Multiply each y coordinate in the parent graph by a. If a is positive, the graph opens up. If a is negative, the graph opens down. Change the signs, either plus or minus, of all the y coordinates. So now we're going to look here. If we have y is equal to absolute value of x plus k, this k is on the outside of the absolute value. That means it's going to be affecting the y's. So if k is positive, move all y coordinates k units up. If k is negative, move all y coordinates k units down. Add or subtract k to each y coordinate. So, now we have here our h. Y equals absolute value of x minus h. If y equals absolute value of x minus h, move all x coordinates h units right. If y equals absolute value of x plus h, move all x coordinates h units left. Now notice here, this does what you would think that it would. So when k is positive, you move it up. When k is negative, you move it down. Here it does the opposite of what you think it would. If you're subtracting h from x, you're moving it right. If you're adding h to x, you're moving it left. All right? So x's are weird. We will talk about this more in class. Set the part inside the absolute value bars equal to 0 to solve for h. Add or subtract h to all x coordinates. For the next few problems, we're going to be doing all the odd problems together, and I'm going to ask you to try all the even problems on your own. Let's start with the first one. We have y equals absolute value of x minus 1 plus 2. Based on what we were just saying, we know the original parent function of the absolute value looks like this. I'm going to draw this as a dotted line. So since we have this minus 1, that means we are moving this 1 to the right because remember we do the opposite of what we think for x is, and then we move it up 2. So this is where our new function will be. Since there's no a out front, it's still just 1, we keep the same slope. So this is our function right here. I'm going to erase what our original parent function was because it's not necessary. Another way you could have done this exact same problem is by making a table. If you were to make a table, what you are going to want to do is you're going to want to see, okay, my x's are going to be 1 to the right. So you're going to want to put 1 in the middle because this is where our vertex is going to be. From there, you're going to want to plot 2 points lower and 2 points higher. That is how you decide what number goes in the middle. From here, if we were to put negative 1 in here, negative 1 minus 1 is negative 2. Absolute value of negative 2 is positive 2. Plus 2 is 4. If we were to put 0 in here, 0 minus 1 is negative 1. Absolute value of negative 1 is 1. Plus 2 is 3. We put 1 in. 1 minus 1 is 0. Absolute value of 0 is 0. plus 2 is 2. 2 minus 1 is 1. Absolute value of 1 is 1, plus 2 is 3. 3 minus 1 is 2. Absolute value of 2 is 2, plus 2 is 4. Which, if you see here, these points all match up with what we just graphed already. Our vertex, as you can see, is right here at 1, 2. Our slope is 1. Our domain is all real numbers, because you can see it goes to the left forever and it goes to the right forever. Our range in this case, remember we moved it, so it changed from our original parent function. Its y is greater than or equal to 2, which you could also write like this. And our zeros, we have none. Nothing crosses the x-axis. Try the next one on your own. When you try this one on your own, keep in mind we have x plus 3, which means now we're moving this to the left. Now let's look at number 3. So you can see here, first I'm going to worry about everything besides the fact that our a is negative 3. So I see that there's no number in here, which means we're not moving it to the right or left, but we have a minus 1 here, which means we're moving it down 1. So this is going to be where our vertex is. Now we have negative 3. This negative tells us it's going to point down. This 3 tells us our slope is going to be 3. So now we're going down with a slope of 3. So it's going to end up looking like this. Again, if we were to make a table, the other way of doing this, we already know where our vertex is at 0, negative 1. So since x is equal to 0, that's what we're putting in the middle, 0. We want to graph 2 things below, 2 things above. When we put negative 2 in for x, we get absolute value of negative 2, which is 2, times negative 3 is negative 6, minus 1 is negative 7. We put negative 1 in here. Absolute value of negative 1 is 1, times negative 3 is negative 3, minus 1 is negative 4. Put 0 in. Absolute value of 0 is 0. 0 times negative 3 is 0, minus 1 is negative 1. We put 1 in. Absolute value of 1 is 1, times negative 3 is negative 3, minus 1 is negative 4. And we put 2 in. Absolute value of 2 is 2, times negative 3 is negative 6, minus 1 is negative 7, which we see here lines up with all the points that we already have. We can see our vertex is 0, negative 1. Our slope is negative 3. Our domain, all real numbers. Our range is now y is less than or equal to negative 1, which you could also write like this. And our zeros are we have none because none cross the x-axis. So now recapping. If we go back, we see here, this opens up, has a positive slope with no number here, so it has a regular slope of 1. And these are all of our function characteristics. And here, this has a slope of negative 3, which is why it's pointing down, and we can see that it got narrower. Now let's go on to the next one. Write the equation of the graph. So we can see here that we have a vertex of 2, 3. So it moved to the right 2, and it moved up 3. We can see that it has a slope. It crosses, looks like right here. So we're going down 3, left 1, 2, 3, 4, 5. So we can see that our A is going to be negative, first of all, because it's pointing down. If we're going down 3, left 5, that means it's going to be negative 3/5. Our H, since we're moving it to the right 2, is 2. Okay, don't get confused that we subtracted the h before. If h is positive 2, our equation would end up being x minus 2 because we know our original parent function. We'll explain this more in class. K is equal to 3 because we are going up 3. And our vertex is 2, 3. All our vertex is h and k combined. So our equation, first of all, our original parent function is y is equal to a absolute value of x minus h plus, use the wrong line, plus k. So that's why when we put positive 2 in here, it's x minus 2. So the equation is y is equal to negative 3/5 absolute value of x minus 2 plus 3. And that's our equation. Our domain is all real numbers. Our range is y is less than or equal to 3, which you could also write as negative infinity to negative 3. It is increasing from negative infinity until 2, which you could also write like this. And it is decreasing from 2 to infinity, which you could also write like this. Try the last one on your own, and we will talk about this more in class.